All right, let's shrink down to the molecular level today as we take a deep dive into molecular analysis. It's like detective work, but instead of fingerprints and footprints, we're using light and heat and even electrons to uncover the secrets of molecules.
It's amazing how scientists can identify unknown substances or, analyze complex materials like polymers and even uncover evidence in forensic investigations, and all by examining the tiniest building blocks of matter.
Yeah, exactly. And we're going to explore the whole arsenal of techniques that make this possible, from shining light on molecules with spectroscopy to, zooming in with electron microscopy.
It really is fascinating. And what's really cool is that even though these techniques operate at the atomic level, their impact is felt in everyday life. What we learn about molecules in the lab translates to advances in, medicine, material science, and so many other fields.
Okay, so let's start with spectroscopy, which is all about how matter interacts with light, or more accurately, electromagnetic radiation. It's like shining a flashlight on a molecule and seeing what colors it absorbs or reflects.
Right, and just like our fingerprints are unique, molecules have their own distinct spectral fingerprints. By analyzing how a molecule absorbs or emits different wavelengths of light, we can identify it and learn about its structure.
So we're basically decoding the secret language of molecules using light. Now, I remember from chemistry class that molecules have different energy levels. How does that come into play here?
Those energy levels are crucial. Imagine a molecule as a tiny staircase with each step representing a different energy level. When a molecule absorbs light, it gains energy and its electrons jump up to a higher step. And when those excited electrons drop back down, they can emit light, creating an emission spectrum.
Okay, that's a helpful visual. So different molecules have different staircases, and that's why they interact with light in their own unique ways.
Precisely. And the type of light a molecule absorbs or emits depends on the energy gaps between those steps. For example, electronic transitions, which involve electrons jumping between energy levels, typically occur in the ultraviolet and visible regions of the electromagnetic spectrum. That's what UVV's spectroscopy is all about.
Uh, that reminds me of something else we're covering today, electronic spectroscopy. So we're using UVV's light to learn about the arrangement of electrons within a molecule.
You got it. And it's incredibly useful for studying things like conjugated systems, which are chains of alternating single and double bonds.
Conjugated systems. Now, those sound familiar. Don't those play a role in things like color?
Absolutely. Think about the vibrant colors of fruits and vegetables. Many of those colors are due to conjugated systems within the molecules that absorb certain wavelengths of light and reflect others, giving the fruit or vegetable its characteristic color.
So a longer conjugated system means more absorbed wavelengths, which leads to even more vivid colors. It's like nature's own light show.
That's a great way to put it. And by analyzing the wavelengths of light absorbed by a substance, we can even use something called the Beer-Lambert law to figure out its concentration.
Okay, now that sounds intriguing. Tell me more about this Beer-Lambert law. It sounds like something out of a detective novel.
It might as well be. The Beer-Lambert law tells us that the amount of light absorbed by a substance is directly proportional to its concentration. So if we know the absorbance of a solution at a specific wavelength, we can calculate exactly how much of a particular molecule is present.
Hold on, so you're telling me we could shine a light through, say, a glass of wine and figure out exactly how much alcohol is in it?
In theory, yes. Of course, there are other factors that can influence absorbance, but the Beer-Lambert law provides the foundation for many analytical techniques. It's like having a molecular measuring stick.
That's incredible. It's amazing how something as simple as shining a light through a substance can reveal so much about it. Now, we've talked about electronic transitions and UVV spectroscopy. What about those other energy levels you mentioned, the ones that involve atoms jiggling and vibrating?
That's where infrared, IR spectroscopy comes in. IR light interacts with the vibrations of atoms within a molecule. It's like shining a light on a tiny spring system and seeing how it responds.
So instead of electrons jumping between energy levels, we're now looking at atoms moving within a molecule.
Exactly. Each type of bond and functional group in a molecule has a unique vibrational frequency, which means it absorbs IR light at specific wavelengths. By analyzing those absorption patterns, we can identify different types of bonds and even distinguish between different molecules.
So each molecule has its own unique dance routine under the influence of IR light.
That's a fun way to think about it. And just like with electronic spectroscopy, the pattern of absorption bands in an IR spectrum acts like a fingerprint for the molecule.
I remember learning about two important molecules, carbon dioxide, CO2, and water, H2O, that have different responses to IR light. Could you refresh my memory on that?
Absolutely. CO2 has a linear structure and its symmetric stretching vibration, where the oxygen atoms move outward simultaneously, doesn't change its dipole moment. This means this particular vibration is IR inactive, meaning it doesn't show up in the IR spectrum.
So it's like CO2 is doing a silent dance move that the IR light can't detect.
Exactly. On the other hand, H2O, with its bent shape, has vibrations that do change its dipole moment, making it very IR active.
So H2O is putting on a much more noticeable show for the IR light.
You could say that. This difference in IR activity between CO2 and H2O is actually quite important. It helps us understand why CO2 is a greenhouse gas, as it can absorb and trap heat in the atmosphere.
Wow, that's a great example of how understanding molecular vibrations at a fundamental level can have real-world implications. It's incredible how much information we can glean from these tiny movements.
It really is. And these are just a few examples of the many types of molecular analysis techniques we can use to unlock the secrets of matter.
This is fascinating. We've covered so much ground already, but I'm eager to dive into the more applied techniques. What's next on our molecular adventure?
Welcome back to our molecular deep dive. We've been exploring how scientists use light to unravel the mysteries of molecules, and now it's time to shift our focus to some real-world applications of these techniques.
Yeah, I'm ready to see how this all plays out beyond the lab. We've talked about the principles of spectroscopy, but how are these techniques actually used to solve problems and, advance our understanding of the world around us?
Well, let's start with electronic spectroscopy, specifically UVV spectroscopy, which you mentioned earlier. This technique is a workhorse in many fields, from pharmaceuticals to environmental science.
Okay, so we're shining UVV's light on a sample and looking at how much light is absorbed at different wavelengths. What kind of insights can we gain from that?
A lot, actually. For example, in the pharmaceutical industry, UVV spectroscopy is used to quantify the amount of active ingredient in a drug formulation. This is crucial for ensuring quality control and making sure patients receive the correct dosage.
So it's like a molecular quality check, making sure each pill has the right amount of medicine.
Exactly. And in environmental science, UVV spectroscopy can be used to measure the concentration of pollutants in water samples. By shining light through a sample and analyzing the absorption spectrum, we can identify and quantify specific pollutants like pesticides or heavy metals.
That's amazing. It's like using light to track down invisible threats in our environment. It makes you realize how powerful these techniques are for protecting public health and the planet.
Absolutely. And speaking of protecting the environment, UVV spectroscopy is also used in the development of new materials like solar cells, which can help us transition to cleaner energy sources.
Oh, that's right. I remember reading about how the efficiency of a solar cell depends on the material's ability to absorb sunlight and convert it into electricity. So UVV spectroscopy can help scientists find the best materials for maximizing that absorption.
Precisely. By analyzing the absorption spectra of different materials, scientists can identify those with the ideal electronic properties for efficient solar energy conversion. It's all about finding the right match between the material's energy levels and the wavelengths of sunlight.
It's fascinating how this fundamental knowledge about molecular energy levels translates into real-world solutions for some of our biggest challenges. Now let's move on to another type of spectroscopy. We discussed vibrational spectroscopy, specifically infrared IR spectroscopy. What are some of its practical applications?
IR spectroscopy is incredibly versatile. One of its most common applications is in identifying unknown compounds. Just like a fingerprint can identify a person, the IR spectrum of a substance can be used to identify it.
So it's like having a molecular database of fingerprints for thousands of different compounds.
That's right. And when an unknown substance is found, its IR spectrum can be compared to this database to see if there's a match. This is used in everything from forensic investigations to quality control and manufacturing.
Wow, so it's like CSI, but at the molecular level. What other detective work can IR spectroscopy do?
While IR spectroscopy is also used to monitor chemical reactions. By tracking changes in the IR spectrum over time, we can see how reactants are being consumed and products are being formed. It's like watching a molecular movie of the reaction unfolding.
That's incredible.
Right.
It's like having a front row seat to the molecular dance of a chemical reaction. I can imagine this would be invaluable for chemists trying to optimize reaction conditions or develop new catalysts.
Exactly. And in the realm of art conservation, IR spectroscopy can help analyze the pigments and binders used in paintings, providing insights into the artist's techniques and the authenticity of a work of art.
It's amazing how this one technique can be applied to so many different fields. It's like having a Swiss Army knife for molecular analysis. Now, I'm curious to learn more about another technique we mentioned earlier, dielectric thermal analysis, or DETA. It sounds like a powerful tool for analyzing polymers, those versatile materials that are literally everywhere in our lives.
You're absolutely right. DETA is essential for understanding how polymers behave under real-world conditions, particularly how they respond to heat in electric fields.
Okay, remind me how DETA works. It's like a two-in-one deal, right?
Yes, it combines thermal analysis, which looks at how a material's properties change with temperature, with dielectric analysis, which focuses on how a material responds to an electric field. By applying both heat and an electric field to a polymer sample, we can gather crucial information about its structure and behavior.
So we're essentially stressing the polymer out by subjecting it to heat and an electric field and then seeing how it reacts.
In a way, yes, we're trying to push the polymer to its limits and understand its response. This is especially important for polymers used in applications where they'll be exposed to extreme temperatures or electrical currents.
That makes sense. Can you give me some examples of how this information is used in practice?
Absolutely. DTA is widely used in industries that rely on polymers from packaging to electronics. For example, it can help determine the glass transition temperature of a polymer, which is the temperature at which it transitions from a rigid, glassy state to a more flexible, rubbery state.
Oh, I remember learning about that in materials science class. Knowing the glass transition temperature is crucial for designing products that can withstand specific temperature ranges.
Exactly. Think about a plastic water bottle. You want it to be rigid and hold its shape at room temperature, but also be flexible enough to withstand some squeezing without shattering. DETA can help ensure that the polymer used for the bottle has the right glass transition temperature for its intended use.
That's a great example. So DTA is like a quality control measure, making sure that polymers meet the necessary standards for their applications.
That's a big part of it, but it's also a powerful tool for research and development. For example, DETA can be used to study the curing process of polymers, which is the chemical reaction that transforms a liquid resin into a solid material.
So it's like watching the polymer solidify in real time and understanding the factors that influence that process.
Precisely. And by optimizing the curing process, we can create polymers with specific properties like increased strength, flexibility, or resistance to heat and chemicals.
This is incredible. We've gone from shining light on molecules to applying heat in electric fields. And it's clear that each technique provides a unique piece of the puzzle when it comes to understanding the molecular world.
And we're not done yet. We still have one more powerful tool to explore electron microscopy, which takes us to a whole new level of magnification.
I'm ready to zoom in even further. Let's dive into the world of electron microscopy and see what other secrets we can uncover. Welcome back to our molecular deep dive. We've explored the power of light and heat to unravel the secrets of molecules, and now it's time to enter the realm of the ultra-tiny with electron microscopy.
Yes, we're going to zoom in beyond what's possible with traditional microscopes and see the world at the nanoscale.
Okay, I'm ready for this close-up. Remind me again how electron microscopy differs from traditional light microscopy.
Well, as the name suggests, instead of using light to illuminate a sample, electron microscopy uses a beam of electrons. Electrons have a much shorter wavelength than light, which means they can resolve much smaller details.
So it's like using a super-powered magnifying glass that allows us to see things we could never see with our own eyes.
Exactly. With electron microscopy, we can see things as small as individual atoms. It's like having superpowers of vision.
That's mind-blowing. We talked about scanning electron microscopy, or SEM, earlier. Can you give me a quick refresher on how that works?
Certainly. In SEM, a focused beam of electrons is scanned across the surface of a sample. As these electrons interact with the sample, they generate various signals, including secondary electrons and backscattered electrons, which are then detected and used to create an image.
So it's like the electron beam is sweeping across the surface, revealing its hidden landscape.
That's a great way to put it. And the beauty of SEM is that it provides a three-dimensional view of the surface with incredible detail and depth.
We've all seen those amazing SEM images of insects, pollen grains, and even microchips. What other real-world applications does this technique have?
SM is an invaluable tool in a wide range of fields. In materials science, it's used to analyze the microstructure of metals, ceramics, and polymers, helping us understand their properties and how to improve them.
So if we're developing a new type of steel for a bridge or a spaceship, we could use SEM to examine its structure at the nanoscale and make sure it meets the necessary strength and durability requirements.
Exactly. And in the field of nanotechnology, SEM is crucial for visualizing and manipulating materials at the atomic level.
That's incredible. It's like we're entering a new era of engineering where we can design and build things from the ground up, atom by atom.
Precisely. And in the realm of forensics, SEM is used to analyze trace evidence, such as fibers, hairs, and paint chips, helping investigators solve crimes.
Wow, so it's like a high-tech detective's toolkit. It's amazing how this one technique can bridge so many different disciplines.
It really speaks to the power of visualization. Being able to see the world at the nanoscale opens up endless possibilities for discovery and innovation.
This deep dive has been an incredible journey. We started by shining a light on molecules, then applied heat and electric fields, and finally zoomed in with electron beams. It's amazing how each technique provides a unique perspective on the molecular world.
And it's important to remember that these techniques are constantly evolving. Scientists are developing new ways to probe the secrets of matter, pushing the boundaries of what we can see and understand.
It's exciting to think about all the discoveries that await us as we continue to explore the molecular world. And who knows, maybe one day you, our listeners, will be the ones making those groundbreaking discoveries.
So stay curious, keep exploring, and never stop asking questions. The universe is full of wonders waiting to be uncovered.
Thanks for joining us on this deep dive into the fascinating world of molecular analysis. We hope you enjoyed it.